Suppose f is a function from a to b, and r is a relation on a. So we have the following picture. We have a one set a and another set b, and a function f from a to b. And we have a relation already defined on the set a, and then we're going to define a new relation s over here on the set b as follows. If we're trying to figure out whether x and y are related by s, so we have an x and a y over here in b, then well, we're going to look and see whether there exists a u and a v back here in a, such that f of u equals x, so u maps to x via f, and f of v equals y, and u and v are related by r. So we have this arrow with respect to the relation r. Okay, so under those circumstances, then we're basically defining x and y to be related by s. Okay, so two elements in B are related by s if we can find some pre-images of them in A which are related by r. Okay, now there might be other things over here which map to x besides u, and there might be other things which map to y besides v, but we don't have to care about those as long as we can find two pre-images of x and y which are related. Then we're good, even if the other pre-images are not related by r. Alright, so our first question is, if r is reflexive, must it be the case that s is reflexive? Well, the answer is no, and I've written out a counterexample over here on the right. Let me go ahead and draw a picture of it. Okay, so if we start off with, once again, sets a and b, and a is going to contain just the number 0, b is going to contain 1 and 2, and the relation r, well, there's not too many things it could do. Okay, we do want it to be reflexive to have a counterexample, so it will just contain the ordered pair 0, 0. And my function f from a to b is just going to map 0 to 1. All right, so f is the ordered pair, set containing just the ordered pair 0, 1. Now let's figure out what the relation s would be on b. Basically, it's going to be the set of all, well, okay, so xy is in s if there's some u and v in a, right, and the only possibility for them is 0, right, so they both have to be 0, such that f of u is x, f of v is y, and uv is in r. Okay, now 0, 0 is in r, so we can just ignore that part of the conjunction. All we require is that f of 0 equals x and f of 0 equals y, and therefore x and y both have to be 1. Okay, so basically s contains just this loop here. Okay, 1 is related to itself by s, but 2 is not related to anything. In particular, it's not related to itself. And because 2, 2 is not in s, that means s is not reflexive. Okay, well, we're also going to ask about whether s has to be symmetric and transitive when r is. And so let's look at symmetric first. And this one does happen to work out. So now before we work out the logical details, let's draw another picture. It's actually, I think, easier to understand visually. So I have a and b again, my function f, my relation r that I'm starting with, and my new relation s I'm defining. And to decide whether s is symmetric or not, we're supposed to suppose that we have a couple things that are related. I think we're going to call them x and y again. Okay, and we want to know whether y is related to x, right? Whether this arrow goes the other way as well. And okay, well, what does it mean that we have xy in s? It means that there exists a u and a v back here, such that u maps to x, v maps to y, and moreover, u is related to v in r, right? All right. Well, here's where we use our assumption that r is symmetric. Right? If we have uv in r, then we also must have vu in r. And if that's a v, and if we have vu in r, then by definition of s, we must have yx in s. Okay, so S is symmetric as well. So, what have we done in this defining S? We sort of pushed forward this relation R on A to a relation S on B, and then to figure things out about it, we sort of pulled back the xy to uv and then used the symmetric property here and then pushed that result forward again to get a result on S. Okay. All right. Well, let's let the symbols fly around for a moment. So we want to assume that R is symmetric. I used u and v there. And prove that S is symmetric, we'll use x and y. We'll let x and y be arbitrary elements of B, and we'll suppose that x s y, and we'll prove that y s x. Okay. So for that, we can use our definition of S up here to write out what that means. And similarly for x s y, I've used u and v here and u prime v prime over here, just to be safe. And we can do existential instantiation on our given side to get a u0 v0 in set A, such that u0 maps to x, v0 maps to y, and u0 and v0 are related by R. Think back to the picture. It's the same thing's going on as we saw there. Okay, and then now that we have u0 v0 in A, we can do universal instantiation to get that. If we have the arrow in one direction, we must have the arrow in the other direction as well in R. Okay, and just break up that conjunction a little bit. And modus ponens will give us the arrow in the other direction. And so it's looking like our u prime is going to be actually v0, and our v prime is going to be u0. Right, because we want v0, u0, and r. That should match up with this statement here. Okay, and so I'm just going to take those and put them in the other order so that they'll match the order here, right? If the v0 is going to be u prime, then and the y is y, then those will match up nicely. So I have all three of these things now, and I do have that u0 and v0 are in A. Maybe you want to switch the order of those two, v0 and u0 in A. And those three things together give us our existential statement. Okay, so that's the proof. It's written out in English over here. So symmetric property is preserved by pushing forward a relation in this manner. How about transitivity? Well, it's not. Okay. So I've written out a counterexample down here, and let's draw a picture of sort of shows why transitivity does not have to be preserved. Okay, so here's my A and my B function f, and when I came up with this one, I sort of was thinking backwards. So you have your 0, 1, and 2 over here in B. And so I was imagining, remember I want S to not be transitive. So I was imagining that I have 0 related to 1, 1 related to 2 in S, but I do not have 0 related to 2. Okay, so S is going to be not transitive. Sort of legible. Okay. But then I wanted R to be transitive, and I wanted it to induce this particular S. And so what I did was I just thought, oh, I'll kind of break 1 in half. Okay, so break it up into an A and a B, and then I still have the 0 and the 2. And my function f is going to map 0 to 0. It's going to send both A and B to 1, and it's going to send 2 to 2. And my relation R is going to have just 0 to A and B to 2. Okay. Remember, that's what we start with. And then I claim that if you start with that R, then this is the S you get, right? Because, well, 0 to 1 is 0, 1 is an S because we can find preimages of 0 and 1 which are related by R. And 1, 2 is an S because we can find preimages of 1 and 2 which are related by R. But 0 and 2 are not related because, well, the only preimage of 0 is 0, the only preimage of 2 is 2, and 0 and 2 are definitely not related by R. Okay, but if you look at R, it actually is transitive. And I've said over here it's sort of vacuously transitive, right? Because there's no way to sort of match up an arrow from the first thing to a second thing, and then from that second thing to a third thing, because we've sort of split up this central element here. Okay, so there's really nothing to prove for R to be transitive. The antecedent of that conditional statement is never true. So there's our counterexample, and that means we're done.